Welcome all of you. Now we are going to discuss the concept called as curl. To understand the concept of curl, this is similar to the divergence which we have derived in the first unit. In the second unit, magnetostatics, there is a new concept called as curl. There the divergence is given as del dot d bar. Del dot d bar. That means divergence is only a two-dimensional quantity which is given by dot product. But curl is a three-dimensional quantity. That means whichever the surface you are considering, on that surface, curl will be perpendicular to that. That means instead of writing the dot product, we should write the cross product for that. That means if del dot d bar will give you divergence of a vector, then del cross d bar will give you the curl of this vector d bar. Okay. Anyway, to understand this curl, first we need to apply Ampere's circuital law to a differential surface element. See, in the previous derivation, we have applied Gauss law. For a differential volume of the element. That volume shrinks to zero slowly. Now, to obtain the concept called as curl, we are using a Ampere's circuital law which is applied to a differential surface element. Here only we will consider a small surface. That surface will have a closed path called as Amperian path, which we have already defined in our previous derivations. There, while applying Gauss law, we are considering Gaussian surface. Here, while we are applying Ampere's law, we will consider Amperian path. Okay, that Ampere's law is applied to a differential surface element. Now, to understand the concept of curl, first we should apply the Ampere's circuital law to a differential surface element. Let us consider a differential surface element like this. The three-dimensional system X, Y, Z. Consider a Amperian path. That means a closed path A, B, C, D, which I am taking in anti-clockwise rotation. Okay, A, B, C, D. This is the closed Amperian path. Now let us consider a point P. What is our aim? By using Gauss law, we should find the electric flux density d bar at some point P. By using Ampere's circuital law, we should find magnetic field intensity h bar at some point P. Let us take that this point P is exactly at the center of this Amperian path that you are considering. That means exactly at the center means it should match the dimensions. This point P is exactly at the center of this Amperian path that you are considering. Let us take that the breadth of this is delta y. The length and breadth are delta x and delta y. Because this BC side and this DA side are matching with x-axis. That's why I am taking this length as delta x, and this AB or CD are matching with y direction. So I am taking delta y. Now for this Amperian path, if I apply Ampere's circuital law and if I want to find the magnetic field intensity h bar at this point P. Already we have seen number of derivations for finding h bar by using Ampere's circuital law. In the similar procedure, again we will find magnetic field intensity h bar at this point P by using Ampere's circuital law, and the path here that you are considering is A, B, C, D, which is kept in xy plane. Your Amperian path is kept in xy plane. Okay. So, what does Ampere's circuital law state? Ampere's circuital law states that the closed line integral of magnetic field intensity h bar around a closed path is equal to the current that is flowing in that path. Okay, the line integral of magnetic field intensity around a closed path h bar dot dl bar is equal to the current that is flowing in that path. Okay, the closed line integral of h bar magnetic field intensity around a closed path h bar integral h bar dot dl bar should be equal to the current that is flowing in that path. This is the Ampere circuital law integral form, mathematical representation of Ampere circuital law, which we have already proved in our previous derivations. Now, what is meant by current density J? Current density J is given as the current that is flowing divided by the surface area. Surface area. That means I equal to J into surface area that you are considering. So, in integral form, can I write the current that is flowing in this Ampere path as integral J bar dot ds bar, where J is the current density. I equal to J current density into surface area means differential surface area. As we are considering only a small differential surface among the complete surface of the element, we are considering only a small differential surface. That's all. I am not considering the complete surface. For that small differential surface, the current is given by integral J bar dot ds bar. Okay. So these two expressions are to be remembered. So what are those? Line integral of h bar dot dl bar is equal to the enclosed current, and the current is given by I equal to integral J bar dot ds bar. Now, for this complete Amperian path A, B, C, D, for this complete Amperian path A, B, C, D, if I want to calculate the magnetic field intensity H, magnetic field intensity H at a point P, the total magnetic field intensity H bar at a point P is given as this is differential surface, we can write it as x component as hx naught into ax plus hy naught into ay plus hz naught into az. This is the complete magnetic field intensity formula H bar at this point P. Similarly, how can we write the current? Current is equal to integral J bar dot ds bar. So I should define J also, current density J. That J can be defined as J bar equal to x component of Jx Ax bar plus Jy Ay bar plus Jz Az bar. So to apply both these formulas, I have defined H, and for this formula I have defined J. Now if I find some useful expressions for these, I can create the concept called as curl. Okay. Now here I want to find the magnetic field intensity H bar at this point P, which is exactly at the center of this Amperian path ABCD. That means path AB, path BC, CD and DA. All these four paths will have their own influence on this point P. Okay. So for that, what are the expressions that we are using here? Line integral of h bar dot dl bar is equal to the enclosed current I, and I is equal to integral of J bar dot ds bar. These are the formulas that we are going to use here. Now, to find the magnetic field intensity H bar at this point P, which is exactly at the center of this closed Amperian path, differential surface element, we should find H bar due to each side separately, due to each path separately. That means H bar due to AB, H bar due to BC, H bar due to CD, and H bar due to DA. All these separately we need to find. So first you consider path AB. First I am considering path AB. Okay. For the path AB, AB is matching with which axis? Y axis. Okay. AB is matching with Y axis. So H bar is equal to some constant Hy, and what is the unit vector in this direction? Ay bar. Okay. Similarly, To apply this Ampere's law, we should also know what is the differential length dl bar. So what is the differential length dl bar? Differential length dl bar, when you are looking for this side AB or path AB length is taken as delta y. Its magnitude is delta y. And what is the unit vector? Unit vector is ay bar. Okay. Now to apply Ampere's circuital law, I need to find the h bar dot dl bar. H bar is equal to hy into ay bar dot dl bar is equal to delta y into ay bar, where h bar dot dl bar is equal to, what is ay dot ay? The dot product of two similar unit vectors is equal to 1. Ay dot ay is equal to 1. So if you apply that, what is the final expression? Hy into delta y. Now if we find what is the value of this hy for path AB, the magnetic field intensity at point P due to this path AB is given as hy into delta y. Delta y is okay, that is the length of this side AB. What about hy? We should create an expression for this hy. So let us create that expression just like the previous derivation. Hy, that means h at point P due to this side AB, which is along y axis, is given as initial value of the magnetic field intensity along this y axis, which is equal to hy naught plus the rate of change of this h. Rate of change means dou by dou x, like that we should write. The rate of change of this hy with respect to x axis. Why I am mentioning x axis means always your h bar and d bar will be acting perpendicular to the path that you are considering. Suppose if you are using Gaussian surface, d bar should be perpendicular to the surface that you are considering. Suppose if it is an Amperian path, your h bar should be always perpendicular to the path that you are considering. Here your path is AB and the direction of h bar is always perpendicular to this AB. That means this h bar is matching with which direction? X direction. That means it is varying with respect to x. Your hy is varying with respect to x. Dou hy by dou x into what is the distance from point P to this side AB? From point P to this side AB. If you consider the complete length, that is delta x, from this point P to this side means exactly half, because this P is exactly at the center of the Amperian path. Okay, so that is delta x by 2. So this is the expression for hy. Now if you apply that here, you can obtain h bar dot dl bar value for the complete path AB. For the complete path AB is given by hy into delta y, where hy is equal to this. We should substitute that. Hy is equal to hy naught plus dou hy by dou x. So if you are finding the value of h bar dot dl bar at this point P due to this path AB is given by, in the place of hy I am substituting this value hy naught plus dou hy by dou x into delta x by 2. Why we are differentiating the hy with respect to x means, for this Amperian path AB, for this path AB, h bar is acting perpendicular in x direction. That's why this h will vary with respect to x. Okay. So and the distance of the point P from this side AB is delta x by 2. Okay. So I am substituting like that into hy into what is there? Delta y into delta y. Okay. So this is the expression for h bar dot dl bar in the path AB. Now we should find the expression for h bar dot dl bar in the path BC. Consider this direction from A to B, from B to C, from C to D and from D to A. We should find the expressions for all the four sides. H bar at point P due to all the four sides that we are considering. So, first path is over. First path is over, that is from A to B. This is the formula for H bar dot DL bar from A to B. Now the second path is path B to C. That means we should find the expression for H bar at this point P due to this Amperian path BC. Now BC means it is matching with which side? X side. Okay. But it is going in which direction? It is going in negative X direction. If you are coming this side, that is positive X direction. If you are going opposite means that is negative X direction. Okay. So in path BC, see, in your path AB, the expression for H bar dot DL bar is given by Hy naught plus dou Hy dou X delta X by 2 into delta Y. Now I will use the same theory for path BC. For path BC, if I want to find the expression for H bar dot DL bar for path BC, then in BC, what is your H bar? H bar is matching with X direction. BC is matching with X direction, but it is going in negative X. If you come like this, positive X. If you go away like this, that is negative X. That means minus Hx as it is matching with X direction, side BC and Ax. Okay. Minus Hx into Ax. And what is DL bar? DL bar means here differential length is, what is the differential length? Delta X. And what is the unit vector which is matching with X direction? So Ax. Delta X into Ax. Okay. So for path BC, as BC is matching with X axis, you are taking H bar as minus Hax into Ax bar, because it is running away from the X axis, we are taking minus. And DL bar is, differential length is delta X into Ax bar. Okay. Now take the dot product for both this H bar dot DL bar is, that is minus Hx into Ax, because what is the expression for H bar? Minus Hx into Ax. I am substituting H bar as minus Hx into Ax into what is the differential length? Delta X into Ax bar. Delta X into Ax bar. Okay. Now here, if you take the dot product Ax bar dot Ax bar, that is equal to 1. The dot product of two similar unit vectors is equal to 1. Okay. So finally what you will get? Ax bar dot Ax bar is equal to 1. So minus Hx into delta X. So finally what is left out? If you find the dot product for this, Ax bar dot Ax bar is equal to 1 and minus Hx into delta X is left out. Okay. So if we calculate what is the value of this Hx, then you can substitute that Hx here and completely we can get the formula for H bar dot DL bar in the path BC. Okay. So how to find that? How to find that means, see, I want to find the value of Hx. That means here I am writing Hx, that is equal to initial value of the Hx when you are considering for this differential surface element. Initial value of Hx is Hx naught. Okay, Hx naught plus the variation of this dou Hx. The variation of this dou Hx, that means dou Hx. Now, how will be your H bar? For whatever path you are considering, H bar will be always perpendicular to that path. That means H bar will act in perpendicular direction like this. Now, your path BC is like this and your h bar is acting perpendicular to that path. That means this path, this direction of h bar is matching with the which axis? Y axis. So your hy will vary with respect, your hx will vary with respect to which axis? Y axis. So dou hx by dou y. And what is the distance of this point P from this side BC? The distance of this point P from this side BC is equal to delta y by 2, because this is distance from point P to this side is in which axis? It is in y axis direction. That means delta y by 2. Delta y by 2. Okay. Now, if I substitute that, if I substitute this hx value in this h bar dot dl bar for the path BC, then you can get the total expression for h bar dot dl bar in the path BC. So I am finding h bar dot dl bar in the path BC, that is equal to, what is h bar dot dl bar in the path BC? Minus hx into delta x, where minus hx minus hx naught, what is hx? Hx naught plus dou hx by dou y into delta y by 2, that is hx value, into what is there again? Into delta x. So this is Ampere's circuit law application. H bar dot dl bar value from AB side at point P, h bar dot dl bar value from BC side at point P. So two paths are completed. Remaining two paths we should find out. Okay. Remaining two paths means CD and DA. We have obtained already h bar dot dl bar values for two paths, that is from A to B and from B to C. Okay. Now you keep these formulas as it is. Now I am going for third path, that is from C to D. Path C to D. For path C to D, how will be your h bar? H bar C to D means this side is matching with y direction. C to D means this side is matching with y direction. Now C to D means your direction is from C to D, but y axis is like this. So if you are going away, what is the unit vector that you should consider? That is minus ay. Okay. So hy is the expression for magnetic field intensity H on this side CD. As it is going away opposite to the y axis, you should take minus ay. Okay, minus ay. Minus hy into ay. And what is the differential length? The differential length is delta y. Differential length is delta y. Delta y into the unit vector in that direction is ay. Okay. So what is h bar dot dl bar? H bar dot dl bar is for the path CD. For the path CD, as it is matching with the y direction, I am taking, for the path CD as it is matching with the y direction, I am taking hy, and as it is opposite to the y axis direction, I am taking minus ay, that is h bar expression, and the differential length is simply, its length is delta y into the unit vector in this side is ay. Now if you want to calculate h bar dot dl bar, that means minus hy ay. H bar dot dl bar means minus hy ay. And what is differential length dl? dl is delta y ay bar. dl is delta y ay bar. Now we know that ay bar dot ay bar is equal to 1. ay bar dot ay bar is equal to 1. And finally what you will get? Minus hy into delta y. Minus hy into delta y. So to find this hy, Now your hy is to be calculated for which side? For this path CD. Your h is matching with y axis direction, so I am taking hy, its notation. But it is calculated in which path? CD path. So your h is calculated in the path CD. So I am taking this CD. So hy when calculated from the path CD at this point P is obtained as initial value of hy for this differential surface element, that is equal to hy naught plus the variation of this hy component. Hy, how will be your h bar now? Your h bar will be perpendicular to this side. That means it is matching with which direction? It is matching with x direction. So it is varying with respect to x. Your hy is varying with respect to x as it is matching with x direction. So by dou x, and what is the distance of this path CD from this point P? That is equal to distance of this path CD from this point P. P is exactly at the center. Complete length is delta x. Half of this is delta x by 2. Delta x by 2. Okay. This is the expression for hy. And you observe one thing. Here this h bar is varying in which direction? Not in positive x-axis direction. That is varying in negative x-axis direction. Negative x-axis direction means here that rate of change should be kept in negative sign. Okay, if you keep negative sign, then that is valid, because h is perpendicular to the side CD means it is going in which direction? This direction is negative x-axis. So I am showing that rate of change as negative sign. So hy naught minus dhy by dou x into delta x by 2. This is the formula for hy when you are observing the Amperian path CD and you are calculating h at point P due to this Amperian path CD. Okay. Now I am writing the third expression. If I substitute this hy here, integral h bar dot dl bar, when you are observing from the path CD, integral h bar dot dl bar, when you are observing from the path CD is given by, what is the formula? Minus hy into delta y. Minus, what is hy? Hy is equal to hy naught minus dou hy by dou x into delta x by 2 into h bar dot dl bar is equal to minus hy into delta y. Already we have substituted hy value with minus sign. What is left out still? Delta y is left out. So finally delta y. This is the expression for h bar dot dl bar when you are looking from the path CD. When you are looking from the path CD, this is the value of h bar dot dl bar. Similarly, next we should calculate h bar dot dl bar due to the path DA. Okay, let us go for the path DA, which is the last side, path DA. So, if you consider the path DA is matching with which direction? X-axis direction. That too in positive side of the x-axis direction. Now, what is the expression for h bar at this point P due to this Amperian path AD? Due to this Amperian path AD, as it is matching with x direction, you should take hx into, what is the unit vector in x direction? Ax bar. Okay, hx into ax bar. As this is matching with x-axis direction, you are taking hx and the unit vector in that direction is ax. And what is the differential length for that path AD? AD and CD are same, so delta x is the differential path, delta x. And what is the unit vector? Again it is matching with ax, delta x into ax. Now if you find the dot product of this h bar and dl bar, h bar dot dl bar is equal to hx into ax bar dot delta x into ax bar. So what is ax bar dot ax bar? Ax bar dot ax bar, the dot product of two similar unit vectors is equal to 1, and if you remove that, finally what you will get? Hx into delta x. Hx into delta x. Now, if I find the value of this hx, that means h due to this path AD or DA. DA is the actual path. H due to this path DA at point P is to be separately calculated again. That is hx is equal to the initial value of hx for this differential element is hx naught that we have taken from the previous expressions minus, why I am taking, we should take here minus or plus means this, what is the direction of h bar at this path dA? H bar will be always perpendicular to the Amperian path that you are considering. If the h bar is acting like this for this path dA, if you go like this, that is positive y axis. If you go opposite, that is negative y axis. Okay. Now your hx is varying with respect to negative y axis. You are going opposite to the positive y axis, so I am keeping minus sign. Minus dou hx by dou y into what is the distance of this point P from this side dA? This complete length is delta y, so half of this is delta y by 2. Okay, this is the expression for hx, that means magnetic field intensity at point P due to this Amperian path dA. So if I am calculating complete h bar dot dl bar for this path dA, then that can be written as h bar dot dl bar due to this path dA is, what is the formula? Hx into delta x. What is hx? Hx naught minus dou hx by dou y minus dou hx by dou y into delta y by 2 into what is there here? Delta x into delta x. So we have calculated h bar dot dl bar values for the path AB. H bar dot dl bar at this point P, due to AB we have calculated BC, CD and DA. Okay. Now what does Ampere's circuital law state? Ampere's circuital law states that the line integral of h bar around a closed path, that means complete integral of h bar dot dl bar is equal to the current I. Okay, current I. Now if I use this expression for the complete Amperian path, then I can find the h bar value at this point P due to this Amperian path. So here Ampere's circuital law states that complete line integral of h bar around a closed path, integral h bar dot dl bar is equal to the enclosed current I. For this complete h bar dot dl bar, we should add all these expressions. That means h bar dot dl bar due to the path AB plus h bar dot dl bar due to the path BC plus h bar dot dl bar due to the path CD and h bar dot dl bar due to the path DA. So already we have calculated the complete all the paths h bar dot dl bar values. Substitute them here, you will get the complete closed integral value of h bar dot dl bar. So if you substitute all these and if you add all of them, the final expression is closed integral of h bar dot dl bar is equal to dou hy by dou x minus dou hx by dou y. Okay. If you substitute all these values here and if you find their sum, then you can get the simplified value as this. Okay. H bar dot dl bar, integral h bar dot dl bar is dou hy by dou x minus dou hx by dou y into delta x into delta y, where delta x into delta y is the formula for surface area of the rectangular path that you are considering. That can be written as delta s, surface area. Okay, delta x into delta y is the surface area delta s. Okay, keep this expression like this. Total integral of h bar dot dl bar you have calculated. Keep this aside. Now you have calculated only left hand side part, integral h bar dot dl bar. Still what is left? We should find the current I that is flowing in this Amperian path. Okay. So for that what I am doing means, we already know that I is equal to integral of j bar dot ds bar. Now we know that j bar is equal to jx ax plus jy ay. This j is called as current density. I can be written as integral of j bar dot ds bar, where ds is the differential surface area of the element that you are considering. Jz az. Okay. Now, so what is the expression for integral h bar dot dl bar? That is equal to dou hy by dou x minus dou hx by dou y into delta x into delta y. That is also written as closed integral of h bar dot dl bar divided by, if I send this delta x delta y this side, it will become divided by delta x delta y equal to dou hy by dou x minus dou hx by dou y. So here we already got the value of integral h bar dot dl bar as dou hy by dou x minus dou hx by dou y, okay, into delta x into delta y. Now if I send that delta x into delta y to this denominator, then it will become integral h bar dot dl bar by delta x delta y is equal to, your right hand side will be dou hy by dou x minus dou hx by dou y, which is equal to z component of current density. Okay, why I am defining this as z component of current density j means, because we already know that the enclosed current I is equal to integral j bar dot ds bar. Here ds bar can be compared to delta x delta y. If you are looking from z side only, that means if you are looking only from z side, then what is the differential surface area? Delta x delta y. As you are getting the differential surface area as delta x delta y, so your j can be considered in z direction. If your surface is like this, then j is acting in z direction, then the surface area when looking from the z direction is delta x delta y. So I am considering this as current density j in z direction. Okay, I am considering this equation and I am comparing this with this. Then we can say that this is the formula for current density when looking from z side. Similarly, we have calculated the expression for when you are looking from delta x delta y, means this is from z side. If you are looking from z side, this is the formula. What I have obtained here, I am writing here. This is the formula for z in j, current density j in z direction. Similarly, by using the same procedure, we can calculate the j value, current density j value in x direction also. X direction means here we should take the area as delta y delta z. Okay, and this is the formula for that. If you consider the j value in y direction, then what is the formula for area? Delta x into delta z. Okay, delta x into delta z, and this is the partial derivative value. Now if I add all this, because we already know that j bar is jx ax plus jy ay plus jz into az. In the place of jx, jy, jz, I am substituting these values. Okay, this is nothing but cross product of two vectors. That cross product of two vectors is nothing but, we are taking the cross product of del operator, del, and magnetic field intensity h bar, because you are having h bar and dou. Dou operators means del, h bar. So this complete term can be compared to J bar. Current density J bar is equal to curl of h bar. Curl can be represented as cross product of del and h bar. So curl h bar is equal to del cross h bar. Similarly, curl d bar is equal to del cross d bar. Like that we can consider J bar. Here up to this derivation for this Amperian path, J bar or curl of h bar is equal to del cross h bar. So this is the final formula for curl. Okay. So our next concept is we should know the meaning of curl. What is the physical meaning of curl? Already we have derived the mathematical expression for curl. What is the mathematical expression for curl? Curl of h bar is equal to del cross h bar, that is equal to J bar. Okay, curl h bar that is equal to J bar, which is nothing but del cross h bar. Okay, what is the physical meaning of that curl? Means curl is the closed line integral per unit area as the area shrinks to a particular point P. Suppose I am considering a point P here for this differential surface. If your surface is like this, from that point P, curl of h bar will be a vector which is perpendicular to that surface. Okay, curl h bar is defined as del cross h bar, which is equal to J bar. Physically, curl can be defined as curl is the closed line integral per unit area. Closed line integral per unit area as the area shrinks to a point. That means in our previous derivations we have derived the expression for integral h bar dot dl bar divided by the surface area delta x delta y, like that. That means closed line integral of h bar dot dl bar per area as the area shrinks to a point. That physical quantity is called as curl. This curl is always given as a perpendicular quantity to the surface that you are considering. How you can compare this means, if you take any body and if that body rotates about its own axis, then that can be taken as curl. Suppose if you are taking some screw and that screw is rotating about its own axis, then that can be taken as curl. Suppose if you consider vector fields, if you consider curl will exist only if the field is rotational. Okay, this point is very important for bits. If you consider a vector field, curl will exist for that field only if that field is rotational. If curl does not exist, then that field is irrotational. Okay, if curl does not exist, then that field is irrotational. This is very important for your competitive exam bits. We can say that for a vector field, if curl exists, then that field is rotational. For only rotational fields, curl will exist. If the curl does not exist, then we can say that the field is irrotational. Okay, so we can compare all these points with the divergence concept. In the divergence, del dot d bar is the divergence. For curl, we will represent del cross d bar or del cross h bar, whatever the vector you are considering. Dot product gives you divergence, del dot d bar divergence, del cross h bar is curl. Cross product is used for curl concept because curl is a resultant vector which is perpendicular to the surface that you are considering. Okay, that is why it is given as cross product. Now, similarly, during divergence, we have seen divergence theorem, which is used to convert a surface integral to a volume integral. Similarly, here by using Stokes theorem, we can convert a line integral to a surface integral by using Stokes theorem. For that, I am considering a total surface of the body. Instead of considering the total surface of the body, take only a small differential surface. take only a small differential surface with its sides with its surface areas as delta S. These are the small differential surface areas. Okay, small differential surface areas delta S. Now the unit vector that is perpendicular to the surface is an bar. Okay, next, what is the curl formula? Del cross h bar is equal to, we have already defined the curl as closed line integral per unit area. That means integral h bar dot dl bar per area is given as curl. Okay, and what is the unit vector for that curl? It is matching with an bar. So an bar we are taking, and what is the differential surface area? We are multiplying with delta S. So if we consider this dot product del cross h bar dot delta S, that will give you the closed line integral of h bar dot dl bar for this small differential surface area. Okay, so finally we can say that closed line integral of h bar dot dl bar is equal to surface integral of del cross h bar dot ds bar, from which we can conclude that line integral can be converted to surface integral with the help of this Stokes theorem. Similarly, in divergence theorem, we can convert a surface integral to line integral. So this is about the concept of curl and Stokes theorem. By using Stokes theorem, we can convert a line integral of h bar to surface integral of h bar. By this, your second unit is completed. Okay, thank you.